Okay, so week 8 tutorial assignment question number 1 is consider a square of mass m as shown in the figure. Then the length of each side is a, and assume that the mass density is uniform, that is surface mass density or sigma. Now consider the coordinate system shown in the figure with the origin at one corner, that is this is the origin then for your case. Okay, then and the z-axis is perpendicular to the plane of the square, means this is the xy plane, this is x and this is y, and the square is lying on the xy plane. So the z-axis is basically perpendicular to this plane. So now they are asking that will the three principal moments of inertia for the given square about the given origin will be equal or not. And then based on that there are four options given, you have to choose one. Now, for such a case, first of all, you have to first calculate or find out what is the moment of inertia tensor for such a problem. Why I am saying tensor? Because this is a 3D picture, right? Sorry, the picture is not 3D, but the problem will be 3D because you are dealing with a square lying in the xy plane, but then it is also mentioned that there is a third axis, which is the z-axis, perpendicular to the plane. So actually, you have to think in 3D. And then for such a case you have to find out what is the moment of inertia tensor with all the components along x, y, z, etc. And because it is the tensor means it will be represented like a matrix, as I think you have seen in the lecture materials. So you have to first find out that for such a problem, for such a square of length side a and mass m and this uniform surface mass density sigma, and then to calculate the principal moment of inertia. So that is the next step, that will be that once you get the moment of inertia tensor, right, and then to get the principal moment of inertia you have to find out the eigenvalues and eigenvectors corresponding to that, or in some other terms you can also choose to diagonalize the matrix of the moment of inertia tensor, and by doing that you will easily find out what is the principal moment of inertia, because principal moments of inertia comes by simply calculating what are the eigenvalues for the normal moment of inertia matrix representation and the corresponding eigenvector values. So basically those eigenvectors will be your principal axis, or in other words principal axis of the moment of inertia. Okay, so like in the options you can see there are questions about that two principal moment of inertia about principal axis in the plane of the square are equal, but one about the z axis will be different. So they're talking about something called as principal moment of inertia and principal axis. So that is why I am telling you that you have to first find out what is the moment of inertia tensor for such a case. So it will be a tensor quantity. So tensor is represented as a matrix. And because it is a 3D case, you have to consider x, y, z, all the three directions. That means it will be, the matrix will be a 3 cross 3 matrix, right? So the matrix will be something like IXX, and then simply ZX, ZY, ZZ. So this is the 3 cross 3 matrix that you have to first find out for such a problem of a square with these dimensions. And once you get that, you need to find out the eigen value, which are basically your answer to the principal moment of inertia. So principal moment of inertia means the eigenvalue of the moment of inertia tensor. Those are called formally as principal moments of inertia. And if you find out the eigenvectors corresponding to that, eigenvectors, then that will be called the principal axis basically. Okay, principal axis. So thus these two will be related. And now let us try and start solving it. So this is question number 1. So first let me draw a quick diagram. This is the origin 0, 0. It's O. This length is A and this length is also A. And this has a total mass of small m with sigma is the uniform mass density. Is the mass density which is uniform, that means it is the mass per unit area, because this is a square in a 2D plane, that is the xy plane. And z is perpendicular to this square plane of the square. So the mass density will be represented the mass by the area of the square, which is m divided by a squared. Why a squared? Because this is a square. So square area of the square is simply a squared. So that is why sigma equal to m by a squared. So that is something that you can do from here. Now, how do you calculate the moment of inertia in such case? So now, choosing the given origin which is at the corner of the square, at corner, okay, so this is the one, and taking simple x, y and z axis as the basis axis, the representation of the moment of inertia tensor, moment of inertia, I'll write it down in short as MOI, moment of inertia tensor in 3D with respect to the origin. This will be in 3D, so 0, 0, 0 is equal to, so by convention, this is the thing that you have to follow. Because this IXY and IYX are symmetric, so both will be IXY and this will also be IXY. And there will be a negative sign for that. IYY minus IYZ minus IZ minus again ZY is same as YZ, so this is same, and this is IZZ. Okay. So now you see that this term and this term are similar, this term and this term are similar, this term and this term are similar. Basically because these are symmetric, so IYZ basically equal to IZY or IXZ equal to IZX or IXY equal to IYX. Such symmetric thing happens. Now to calculate each of the terms separately, so how should you calculate? So first of all, a small mass element dm will be equal to sigma dx dy. So dx dy is the area element, small area element, infinitesimal area element in 2D. So this is equal to dA. So you can represent it in the present condition as dx dy, and sigma is the mass per unit area. So this mass element, infinitesimal element of mass will be infinitesimal area element times the mass density. So this will give you the dm value. Now the moment of inertia values will be like Ixx, because in xy plane your object, the square, is sitting down. So Ixx will be simply, with respect to x axis, means it is simply y squared dm, right? Because with respect to x-axis, the inertia term will have y square dm. Now, how should you represent dm? So for that you need to include this expression sigma dx dy. So y square sigma dx dy. So sigma dx from 0 to a, and then y square dy from 0 to a. Sigma a minus 0 y cube by 3 a 0. Simply sigma a to the power 4 by 3. Similarly, by the same logic, I will also be x squared dm, and it will be like x squared dx. This is sigma dy in from 0 to a and 0 to a. And because of the symmetry of the square, it will be same as the value calculated for ixx. So it will also be sigma a to the power of 4 by 3. Now by the same rule, you know how to calculate not by the same rule, but izz, you know that you should use the perpendicular axis theorem, that because your square is sitting on the xy plane and z axis is perpendicular to that plane, so by perpendicular axis theorem of moment of inertia, you get izz equal to summation or sum of ixx plus ixy. So this is simply 2 sigma to the power 4 by 3. Now what are the mixed terms? Ixy, suppose ixy will have x into y dm, which is sigma x dx from 0 to a, and y dy from 0 to a, which is sigma a squared by 2 into a squared by 2, which is sigma a to the power of 4 by 4. So because I told you that ixy and iyx will be symmetric, because this is just a product. So product does not matter whether you take x first or y first. These are the same, so this value is the same. Now, but ixz will be 0, because that involves to have a product of x and z, but in this case the square does not have any z component, so the z is already 0. So anything involving the term of z will be giving you the product as 0. Now this will be same as izx. And similarly, Iyz also should have a z term, but z is 0 for this plane of the square. So this is also 0, and this is same as Iz. Now you just have to put all that separate values and then construct the total moment of inertia tensor. First of all, Ixx we got sigma a to the power 4 by 3. Right? Now, if you notice that each of these terms in the moment of inertia tensor has this term common as sigma a to the power 4. All of these terms have them. So, to simplify our problem, we can basically take the sigma a to the power 4 as a common outside the matrix, and then only the numerical terms will be inside, because sigma a to the power 4 is common to all. So, if that is done, then Ixx only have this coefficient of sigma a to the power 4 as 1/3. Right? Now for ixy has a minus sign with that, so ixy is sigma a to the power 4 by 4. Now with sigma a to the power 4 outside and with a minus sign, we are only left with minus 1 by 4. Now this third part has ixz, but you saw that ixz is 0, so this is 0. Now the second part, if you remember, this will be iyx, which is same as ixy, and it will have a minus sign, so minus 1/4. Now iyy is same as ixx, so this is also 1/3, and yz is the third term, which will be 0, because again it has a z component. Right? Okay. So then the last row will be izx or ixz. Both are same. Again it will be 0 because there is no z. Then iyz or zy. That will also be 0 because again no z is there. Then izz is simply 2/3 because sigma a to the power 4 is taken common outside. Now we have finally successfully constructed our moment of inertia tensor matrix representation. Now we just have to diagonalize it, or you just have to simply find out the eigenvector and eigenvalues to have the answer of principal moment of inertia and principal axis. So you know that if you can diagonalize a matrix like this, that only this term, and this term will be here, and all other terms will be 0. So then only the diagonal elements will be there. So then it will be diagonalized form of the same matrix, and the diagonal elements are the eigen values of the matrix. So if that is the case, then you see that we can simply choose to solve the typical math methods problem of how we basically what do I say? How do we basically get the or calculate the eigenvector and eigenvalues for a matrix? So in this case, we will have, let's say the eigenvalue is, so your matrix is I, let's say, and your eigenvector is, let's say, u vector. So you have I u vector equal to lambda u vector, because this is the matrix or operator somewhat, and this is the vector on which it is operating, and it is giving you back the eigenvalue and the same eigenvector. So by this rule, you have, if you take I minus lambda to one side and u vector equal to 0, we'll use directly this. So your I matrix is there and lambda is taken with a minus sign. So lambda means lambda is a constant, right? But I is a matrix. So how do you represent I minus lambda? Basically, because they have to match in the structure, so that you can take a like subtraction between them. So you have to also represent the lambda in a matrix format. So only lambda means lambda into unitary matrix. Okay, sorry, not unitary but unity matrix. So any constant term is simply that term into a unity matrix if you have to really express it into a matrix structure. So if that is the case, you know unity matrix in 3D is only diagonal elements are 1 and all other elements are 0. So this is lambda 1, 0, 0, 0, 1, 0 and 0, 0, 1. So this is lambda 0, 0, 0 lambda 0 and 0, 0 lambda. So you have I minus lambda u. So you have this I 1/3. First minus lambda will be there because you have only lambda in the diagonal terms. So all the other terms remain as it is, and only the diagonal terms are getting changed by a subtraction of lambda. So I hope up to this everything is clear. Okay, and because this is a matrix sort of a thing, you can also say that determinant of I minus lambda, this matrix, will be equal to 0. So if this is the I minus lambda matrix that we have constructed, then you have to say that the determinant of this matrix equal to 0 to actually get the eigenvalue or lambda. Now how do you get the determinant? So this is very simple, that 1/3 minus lambda, then you multiply this into minus this. So then 1/3 minus lambda, 2/3 minus lambda, minus 0 into 0 is 0. So this is one thing. Okay, then the second term will be minus 1/4. Then it will be in the same sequential order. So for this column, you have to first multiply this and then multiply this. Okay, so yeah. Mhm. So the third term will be anyway 0, and the second term will be 0 0 minus something. So this is, sorry, I made a mistake, I think. Just let me check once. Minus 0. Just 1 second. Let me check something and come back. Okay, so basically, let us return to what we are doing. So I was having a confusion with whether I was getting the matrix right or not. So I have checked right now. So this is okay. So as we are discussing the determinant calculation of this matrix, so you will get that this part multiplied with this part minus this part, then this part multiplied with this part minus this multiplication, plus 0 will give you the product also 0. So you have two terms involved. Okay, so now right now you carefully just distinguish from each of the terms and you find out some common factors. So like here this 2/3 minus lambda is common in both of the terms, so you just take it common, and 1/3 minus lambda whole square minus 1 by 16 is written down as 1/4 square. So this is equal to 0. Now this is sort of like a squared minus b squared. So you get the formula of a plus b into a minus b. And right now you get that you get 3 roots of lambda. Each are different from each other, which is 2/3, then 5 by 6, and then minus 1 by 6. And because these are just numerical values, but you remember that your matrix had a term outside, which is the sigma e to the power 4 was outside, right? So each of the eigenvalues will be multiplied by this sigma e to the power 4 as well. So as you know that the eigenvalues of the tensor or moment of inertia tensor are 2/3 sigma e to the power 4 means. So sigma you can now express as m by a square into e to the power 4 is simply 2/3 m a square. Similarly, let's say we call it I1, then the eigenvalue, second eigenvalue is 5 by 6 sigma e to the power 4, which is same as 5 by 6 m a squared. By the same formulation, you just have to put the value of sigma. And the third eigenvalue will be minus 1/6 sigma e to the power 4 equal to minus 1/6 m a square. So you get 3 eigenvalues, and you see that all 3 are different from each other. Okay. And just I have at the first told you that for moment of inertia problems, you have to first find out the moment of inertia tensor. Now to get the principal moment of inertia, you just need to diagonalize it, or in other terms, you just need to find out the eigen values of that moment of inertia tensor that we have already obtained. Those eigen values are actually called the principal moment of inertia. All 3 eigen values or 3 principal moment of inertia are different from each other, and this indicates if your principal moment of inertia are all different from each other, this indicates that your mass distribution with respect to the given origin is not symmetric. Because anyway you could find that out or figure that out by looking at the diagram as well. Because if this is your square in this diagram and this whole mass is distributed over the square plane, but your origin is sitting at the corner of the square, that does not make this mass distribution symmetric with respect to the origin, because origin at the center, at the corner. If the origin would have been at the center, then you could say that the mass distribution is symmetry about this central point. But with respect to this origin, it will always have a non-uniform, different principal moment of inertia values, and which indicates that the mass distribution is not symmetric with respect to the given origin. So that is the answer we have to mark, that all the 3 principal moment of inertia, or in other terms eigen values of the inertia moment of inertia tensor or the matrix, are different from each other since the mass distribution is not symmetric about the given origin. So this is our answer. Okay, and then Okay, so this question is done. So let us move on to the second question now. So second question is saying that this exercise illustrates the matrix nature of the moment of inertia manifested in a non-zero product of inertia. The adjacent figure shows a uniform planar mass distribution in the shape of a right-angled triangle of base b and height h. Assume surface mass density sigma to be unity. Clearly, in the coordinate system shown in the figure, the mass distribution is not symmetric about the coordinate axis. Hence, we expect the product of inertia or Ixy to be non-zero. In this coordinate system, if b equal to 1 meter and h equal to 1.5 meter, then Ixy value will be how much in meter to the power of 4. So first of all, you have to first draw a diagram and let understand what information is already given to us. So second question. So the second question has some sort of a triangle, which is a right angle triangle. So let's say, so this is your y axis and this is your x axis. Okay. And this length is b along the y axis and this length is h along the y axis. Now, for the purpose of the making this problem easier, we have to choose a small element, mass element from this entire structure, because there is a mass distribution will be here. So everything here will have a mass distribution where the surface mass density sigma is taken as unit. Okay, so taken in the question sigma equal to 1, and this small strip has a um, width of dx, and this is sitting at a distance x with respect to the origin. If we say this is your origin, so this is at a distance x and it has a strip of thickness dx. Okay, so if you have to draw its central axis or a central mass point for this strip, so you get two axes. One is this axis, another is this axis. This is y prime and this is x prime. So this is the new axis, because this x and y, apart from that, if you take us through the center point of this mass element strip, if you take two axes, that will be named as x prime, y prime also. So we call, apart from that, we call this length as our y naught, which is this length is also y naught. But from here up to here, from the starting point up to the middle line, this length is, distance is x naught, right? Let us choose that. Now we need to, because again for the moment of inertia problem, it is very important to find out a particular small elemental area, so that the whole calculation becomes simpler. So that we have already done. Okay, so this is a so we are solving this question number 2, where this triangle problem was given and you are asked to calculate the uh, IXY, I think, yeah, you're asked to calculate the IXY answer in meter to the power 4 units. So let us resume that. So this triangle has this, this is the right angle triangle, have this height h and this base length is b. Okay, so to calculate the moment of inertia, sorry, the product of inertia IXY, you choose a small area element inside the triangle which is sitting at a distance x from the origin, and it has a thickness of dx and it has a height of, this height is y. Okay, and uh, this area that this shaded region makes is area of dA, where dA is nothing but y times dx. Y dx, because this on the horizontal side this is dx and on the vertical side this is y. So that is y. And then you can also draw another set of axes through this newly drawn shaded portion or area element, like across the central line of this shaded strip. You can draw the axis of x prime and y prime that is going through, and about this x prime and y prime axis are drawn in such a way that about this the element is symmetric. That means if this is the x prime dashed line and this is the y prime dashed line, this is going right through the center of this mass distribution inside the shaded region, or this makes the this is at a symmetric configuration of this mass distribution on for this area element of area of dA. So that is the advantage. One advantage why we have drawn this symmetry axis is that whenever a mass distribution is symmetric with respect to some axis, then the product of inertia term becomes 0 for the area element on that axis configuration. Means that like in this case, if this we have considered this x prime y prime axis, which is about which this area element is symmetric. So let us say that at a small mass element of area dA equal to y dx is taken at distance x from origin, a distance x from the origin, and we consider from the area about which the mass distribution in area element dA is symmetric. Okay, so now here comes a time where we will use the parallel axis theorem for the moment of inertia, but or the product of inertia. But here, because we are dealing with a small area of dA area, so then we'll use a differential version of the parallel axis theorem. That means that For dA area, apply differential version of parallel axis theorem is that differential of Ixy is equal to differential of I x prime y prime plus x naught y naught sigma dA. So let us call this equation number 1. So if you recall, what is the parallel axis theorem statement was that if you have in one dimension, let's say simple parallel axis theorem is that if you have one dimension and this is one axis and this is another axis, so about this product, if the distance between them is, let's say, r, okay, so let's say about this axis the moment of inertia is I xy, and about the second one is moment of inertia about a new axis is I prime xy. Okay, and they are parallel to each other. So in this case, I xy would be I prime xy plus m r squared in this case. Okay, so by the same so using the same equivalent thing for this small differential area dA, because it is a small area or area element, so that is why everything is taken in a differential form with this d in front of it. So the product of inertia for the small element area dA about this xy axis that was originally there is dxy, right? Dixy. This is the product of inertia for small area element dA and this is product of inertia of this small area element dA about the x prime y prime axis. So this is right, and this whole part is the mass for the small area dA is equal to the mass density per area times the area element, and this x naught y naught is simply the distance of this area element from the xy axis to x prime y prime axis. So along x prime along x to x prime, sorry, between the distance between y prime and y is x naught, and the distance between x prime and x is y naught. So distance between x and x prime axis is y naught, which is this one, and between y and y prime axis is x naught, which is this thing. So now in this equation number 1, in the question it is suggested that we have to take the sigma equal to 1. In that case, dIxy is just d I x prime y prime plus x naught y naught dA. Now bi x prime y prime will be equal to 0. Why? Because this is what I was talking about, that the product of inertia becomes 0 if the axis is such that the area or the mass distribution for that area is symmetry about that axis configuration. So like x prime y prime axis, here you can see the dashed line going through the center, passing through the center of this dashed region of area dA. You can see that the mass distribution or the area dA is exactly symmetric about this x prime y prime axis coordinate, but it is not symmetric for the about the x y y coordinate that is drawn at the corner with the center or the origin at the side of. So that is why the area dA is not symmetry about xy, but the area distribution is symmetry about the newly drawn axis x prime y prime. And the advantage of this choosing this new axis is this, what I have written down below, that about x prime y prime axis, the area element is symmetrically distributed, and you already know that for symmetric distribution the product of inertia will be 0. Why? Because you remember that product of inertia has terms like x dx and y dy integration, where the integration limits, instead of going from 0 to a like in normal case where there is no symmetric mass distribution, so this does not cancel out. But for symmetric mass distribution, this will probably go from minus a by 2 to plus a by 2, or similar for x y direction also. So in such cases, you have x squared by 2 or y squared by 2 going from minus a by 2 to plus a by 2, and because it is a square term, so this gives you 0. So that is why this is a simple idea of how choosing a symmetric axis is important, about which the mass distribution is symmetric, so that we have the product of inertia term to be equal to 0 for that case. So in this case, because we are talking about a differential small area element dA, so we have differential of the product of inertia, that is di x prime y prime equal to 0. Now if you want to find out what is the equation for this triangular things hypotenuse, so that is this axis, this line, so we call it y. So what is the equation for y? So let's say this triangle is A, this is O, and this is B. Hypotenuse AB equal to, it can be, so you can find out the equation for the straight line, because you know its slope and the intercept on the y-axis. So basically you can find out the equation for AB. What will be AB? AB equal to will be some y equal to mx plus c kind of an equation, right? And now you have to just find out what is m and c for this case, like what is m for this line AB. So you can see this line AB has a vertical stretch of h and a horizontal stretch of b. So slope is simple, the vertical by the horizontal distance. So this is, in simple terms, this is h by b slope, and also this is a negative slope because the line is such that the slope is obviously negative. So this is minus of h by b, and c is the y-axis intercept for the line, which is clearly evident from the diagram that is drawn, that on the y-axis it has an intercept of h. So c equal to y-axis intercept equal to h. So now your y equal to minus hx by b plus h, where this is equal to h into 1 minus x by b. This is the equation for the triangle hypotenuse AB. This we call it equation number 2. Now once y is known, then you can find out what is the area element dA. D equal to simply y dx. So y equal to simple 1 minus x by b into h into dx. This is our equation number 3. Okay. So now from the picture, if you again look at it, you will see that this distance of x naught from the symmetric axis of y prime to the original y axis, this distance x naught is same as this distance x. Similarly, this distance from between the x prime and x axis is y naught. That is half of the distance of this full thing, that is basically your y. Right, because this area element has a vertical distance of y, as we have already taken a note of. Okay, and so y naught is exactly sitting halfway to the total distance of y, so y naught equal to y by 2. So x naught is equal to x and y naught equal to y by 2. This is equation number 4. So then d I xy equal to this, using this relation 1, this part is 0 and this part values we know what is x naught, y naught and dA. So then using equation 1, dxy equal to dx prime y prime, di x prime y prime is 0 plus x naught y naught is, x naught is x, y naught is y by 2, and then sigma dA, but sigma was taken as 1, so this is simply dA equal to y dx. These are the formula or the relation that we have used to get to this. Now once this is done, so now this is simple to calculate Ixy by simply taking an integration. So this is so you can convert the whole thing into x, so that only integration is in terms of x, and for that we'll use this equation of this straight line y equal to some terms in terms of x, and this is equation number 2 that we will use. So this is x by 2 and y is h 1 minus x by b. So y squared will be simply h squared 1 minus x by b whole square to dx. So now by simplifying, this is h squared by 2, this is x 1 minus 2x by b plus x squared by b squared dx, where x is going from 0 to b. X minus 2x squared by b plus x cubed by b squared dx. This is from 0 to b. Plus x to the power 4 by from b to 0. So here you have this is h squared by 2 b squared by 2 minus 2 by 3 b squared plus b squared by 4, so x squared by 2, 4, 2b squared, not 4, is equal to 12. So this is squared by 2, squared by b squared by 24. Now you can just simply put your values known about h and b, which are given in the question. So in the question it is given that h equal to 1.5 meter and b equal to 1 meter. So then so this will be your answer. So let us see. So okay, the accepted answer is in the range of 0.092 to 0.096. So we are getting 0.094 meter to the power 4 is equal to dix. So this question is also done. Now third problem. It is saying that the problem deals with a thin plate, which is an example of quasi 3D mass distribution. The upper edge of a thin homogeneous plate is parabolic with a vertical slope at origin O. See the figure. The plate has thickness T, length B, height H, and mass M. The mass density rho of the plate is constant. Its moment of inertia about x-axis will be how much? So this is the diagram they are talking about. This is a very thin plate sort of a thing, and the upper axis on the upper boundary of this plate is going in a parabolic equation form, which is this thing from 0 to this. This is the parabola or parabolic. Okay, and this is the origin O. This is the height of the parabola at the extreme end, which is H, and this horizontal extent is up to B along the x-axis, and so the thickness of this plate is T. Okay, so now to solve for the, and this is the uniform mass density of rho value, which is constant. Then what is the moment of inertia about x-axis? That means they are asking for the ixx value. So let us start solving it. So this is the picture. This is the 3D part. And this thickness is T, this height is Y, this entire height is becoming H, and this entire distance is B, but a small part of thickness or extent of width dx, and up to this is distance x. Now, because this upper boundary is parabolic, for the equation will be the equation of a parabola, where we take y squared equal to kx, where k is unknown constant. And for knowing that, we will apply the boundary condition that at x equal to b, y value is known as h. So then h squared equal to k into b. So k equal to h squared by b. So the parabolic equation will be y squared equal to h squared by b into x. This is equation number 1. So y will be equal to h by root over of b times root over of x. Equation number 2. Y is expressed in terms of x. Now again, for such cases we have to choose the area element and deal with that. So in this case we have already chosen our area element, which is this dashed region. And now the moment of inertia about x-axis is ixx. So what we will do is that we first calculate the moment of inertia about x-axis for the small area element dA, and later on we integrate that to get the ixx for the entire configuration. That is our idea of solving it. So we at distance x from the origin and with equal to dx. So for this part, the volume is, the area is y dx times the thickness, which is basically same as the thickness of the entire sheet. So this thickness will also be t. So this is y t dx. And because the mass density per area is uniform and constant throughout, mass for small element dm equal to rho ty dx. Now dixx is the moment of inertia for the small element of area taken in the diagram. So your dixx will be simply, because you know that ix is equal to y square dm, so in this case this will be simply 1/3 y square dm, because this is a 3D picture, okay, and we are only talking about one axis about which we are calculating the moment of inertia. So that is why, unlike other cases, so it has all three dimensions involved, x, y and z, and it is stretched through all three dimensions, and because of which we have to take this 1/3 factor for getting this dixx, and rest of the things are just 1/3 y square dm, and this is 1/3 y square dm is equal to rho py dx. This is 1/3 rho t y cube dx. So now for entire configuration, ixx which we want to derive is simply integration of dixx, which is nothing but rho t by 3 y cube dx. Now y you can express in terms of x, that is h by root over b root over x. So and the limit of x, that is the integral limit, is x equal to from 0 to x equal to b. This rho p by 3 h cube b root over b. This is x into root over x, making it x to the power 3 by 2 dx from 0 to b. So this is rho t h cube by 3b root over of b, x to the power 3 by 2 plus 1 divided by 3 by 2 plus 1, going from 0 to b. This is rho t h cube by 3b root over b. 5 by 2 by 5 by 2 is basically 2 by 5. This is b to 0. So this is 2 rho t h cube so this whole thing is 2 by 15 rho t h cube to b. 5 by 2 is 3 by 2 plus 1, which is basically b square into root over of b, and now divided by was b root over of b. So this cancelled out and you get your final answer as 2 by 15 rho t h cube b. So this is the final answer of what should be the moment of inertia about not ixy. This is ixx for the entire constellation. So mark this. This is the correct answer we have obtained. Alright, so question number 4 is that the right angle bar rotates clockwise with an angular velocity omega, which is decreasing at a rate of 4 radian per second square. At the instant when the angular speed is 2 radian per second, which of the following are the correct values for the velocity and acceleration of the point A? So this is a right angle bar where this portion is fixed to this and this portion is free to it and perpendicular to it, and about this y prime and this y dashed axis, there is this rotation of this horizontal part of the rod, which will also make the vertical part to rotate as well with an angular velocity of omega. But as per this rotation direction, so if the bar is rotated like this in the clockwise manner as given in the question, so on the next moment after a certain rotation, where it will be, so it will, in the clockwise manner, it will come to here. Okay. So at the same time, if you go on, you will see that position will change for this vertical axis as well. But what is the direction of movement for that axis? Okay, so because that will be simple, because this vertical part is always going towards the vertically downwards direction, which is basically your minus z direction. So that is why your omega for this point A, for this vertical part is equal to minus z direction, so minus and 2 radian per second, and it is negative z direction, so this is 2 k cap. So from here you see that the speed or angular speed using the right hand rule gives omega equal to minus 2 k cap radian per second, and the angular acceleration is also given as Uh, and this has no minus sign, this becomes plus, because otherwise it is said in the question that the rate of decreasing of the angular velocity, that means it is a not an acceleration, it is that is why the sign will be reversed. So this is opposite to acceleration, and that is why there is no negative sign, but it has turned to positive sign, and it is also along z axis. So this is 4 k cap radian per second square. Now the velocity and acceleration of this point A on this rod will be, so they have asked to answer both of the things, velocity and acceleration. So what is velocity first? Velocity velocity at point A to V into omega cross R. V equal to omega is minus 2 k cap cross R vector is, this x distance is 0.4 plus this y distance is 0.3. So this is so instead of taking x cap and y cap, let us choose I cap and j cap to make this consistent. So now you take the cross product. So this is k cap cross I cap is cross product, if you take, is j cap, and there is a minus sign, so this is minus j cap plus minus 0.6 k cap cross j cap equal to minus y cap. So we are getting 0.6 I cap minus 0.8 j cap. So this is velocity, so this will be meter per second. Now for the acceleration, that will be a combination of two parts that is already taught in the lecture. That one acceleration part will be an vector, which is simply omega vector cross r vector, and omega cross r we have already calculated in terms of v. So this is simply omega vector cross v vector, and omega vector is minus 2 k cap as already said, cross product of 0.6 I cap minus 0.8 j cap. So this is k cross I, will making it j, and k cross j is making it minus I, this minus and minus making it plus, so this is minus 1.6 I cap minus 1.2 j cap meter per second square. And the other part of the acceleration will be called as at vector is equal to the angular acceleration alpha cross r vector is equal to plus 4 k cap cross 0.4 I cap so this part, and this is equal to k cross I is plus j cap, k cross j is minus y cap. This is minus 1.2 . So the net acceleration finally be somehow in the order of A vector is equal to A n vector plus A t vector, which is minus, so this plus this. So I cap wise, if you take that, this is minus 1.6 minus 1.2, so this is making it minus 2.8 I cap, and this is minus 1.2 plus 1.6, so this is making it plus 0.4 j cap. This is the final answer. Let's check. So the answer will be this plus 2 minus 2.8 plus 0.4. So this answer 0.6 I minus 0.8 is the velocity, minus 2.8 plus 0.4 is the acceleration. So this question is also solved by the same logic. Now question number 5. So in question number 5, if you look at it, they are saying that 4 equal point masses, each of mass m is located at 4 corners of a square. See this figure. They are attached to an axis, which is the solid line, passing through the center of the square by strings, which is this dashed lines. All the masses are rotating about the axis with the same angular velocity of omega, so that they always remain in the shape of a square. What is the total torque due to the tension in the 4 strings about the center of the square? Hint is that the figure drawn on to the scale start analysis by locating the center of the square, then determine the tension force and the torque due to the tension force for each mass. So they are saying that these 4 masses, if you join them, it is kind of sitting at 4 corners of a square. So imaginarily you can try and join them, so they look like a square, and this central axis is common to all, and with this they are tied by strings, which is this dashed lines. Okay, and they are rotating about this with an angular velocity of omega. So first we have to take a center of mass or a center of square for this case, and then with respect to that we need to solve this. So let us onto a page. So for simplicity of dealing with the problem, we first deal with only 2 masses at a time. So if this is your axis, let's say this is your center of mass. So with respect to this, your A point is, let's say, sitting here, and the B point is sitting there. So this distance, there is a distance here, it's a distance there, this is O, this is the center of mass for the square, and this is the central solid axis. Now because it is said that A and B are sitting on corners of a square, but right now we just deal with, instead of 4 masses, we deal with 2 point masses at a time, and in this figure they are noted as A and B. Now we can draw perpendicular lines. Sorry, this is not perpendicular. So this is your perpendicular 90-degree angle. for this case, this is your 90-degree angle. So you can redraw it once. This will be the 90-degree angle. So this length from the particle direction from say A to the axis point is the particle or the perpendicular length of RA, and this length is from here to here, particle length is RB, and we also call this length as LA, and this entire length is LB. So for simplicity, two out of so this is end point and this is end point. So now for these two masses sitting at point A and point B, they are tied to this main central axis by this solid black line, tied by some strings, right? So and O is the center of mass. By the four masses. Okay, so then the string attaching and mass at A and B to the central axis is equal to defined as OA and OB respectively. Okay, and the perpendicular distances from A to the central axis is AM, that is taken as RA, and the perpendicular distance from B to the central axis into BN is RB, and the distance from O to M is taken as LA and O to N is taken as LB. Now point A, force effectively is equal to FA, will give rise to centripetal acceleration of point mass at A. So that is why the force will be a centripetal force. So F equal to m omega squared Ra. So then the torque for this case about A, or sorry, about the center of mass, that is in this case O of the square. So torque about center of mass for force of Fa, torque is tau A equal to R vector cos of force vector. So if you just bother about the magnitude and not the directional information of this torque, the value will be force times the distance, the perpendicular distance from this center of mass point to the A point. So the vertical perpendicular distance is basically Ra. So this is R becomes Ra, and Fa is already m omega squared Ra. And this will be in a direction, in a certain direction that we get from the cross product, but this value is m omega squared sorry, this is not Ra that we should take, because we are taking this distance, this horizontal distance we need to take, not the vertical one, because you have your center of mass at this point, and on this point you need to find out what is the torque. Okay, so the force it is acting on this direction. So about the center of mass O, and this is the point A, what will be the torque? So tau A will be, if this distance is LA, then LA cross F. So this horizontal distance need to be collected. So this horizontal distance for this case is LA, and for the other case of point mass B, it is LB. So here it is LA. So this R is basically LA. So this is m omega square LA Ra. Now same the torque about due to force AB at B with respect to center of mass equal to O is given as tau B equal to, here the distance R is LB to FB, and FB will be the same as centripetal force like LA, and this is m omega squared RB. This is the total thing becomes m omega squared LB RB, and by the geometrical configuration the direction of tau B will be opposite to the direction of tau A, because the point masses are sitting in the two opposite directions with respect to the center of mass. So the distance factor will be different for both of them, and this will basically change the sign for the cross product of B present in tau A and tau B. So now you have to use something called the law of congruence for the two triangles that is given in this picture. Okay, so in this picture, in this diagram, there are two triangles AOM and BON. Now, how do you know that these two triangles are satisfying the rule of congruence. So you can compare their angles. They have all three angles same. So the rule of AAA, three angle rule for the congruence formula will be satisfied, because this is the right angle and this is also a right angle. And this angle is, let's say, theta. So this angle becomes 90 degree minus theta. But if this is 90 degree minus theta, then obviously this is theta and this is 90 minus theta. You see that three of the angles are matching with each other. So by three angle rule, triangle AOM and BON are um, congruent, and by satisfying the property of congruent triangle, so by its property you can apply the perpendicular axis rule, and because of this you see that you have two direction arm values to be exactly same. Like in this case, this is the perpendicular and this is the perpendicular. Okay, so this RA distance is nothing but same as the LB distance, because this RA is sitting for the triangle AOM. This RA is opposite to the angle of 90 minus theta, and equivalently for the triangle BON, the angle 90 minus theta and opposite side is LB. So because of the congruence relation, now you know that RA equal to LB. And similarly, this opposite to theta for triangle AOM is the length of LA, and opposite to theta for BON, the length is RB. So also this makes tau A equal to tau B, because this has M omega squared common and LA RA and LB RB. So this is M omega squared, LA is RB and RA is LB, and tau B is already that. Tau A equals tau B. And we already stated that tau and tau B, their values are similar. Now we find out that the values are same, but they are exactly opposite directional to each other. That was known from before by looking at the configuration. So cancel each other out, and total torque and now for further complication in the same problem, if you also introduce the other two masses out of these four masses, so for the other two masses the same rule will be followed, and the center of mass for also for the other two masses will also be such that the torque about the center of mass for the rest two masses C and D, let's say, will also be 0. So by similar means respect to center of mass for net torque for the entire square is equal to 0. This is your answer. because they all cancel out each other. So the answer is 0. Okay. Okay. Question number 6 was a small rescue helicopter has 4 blades, each of 4-meter length and the mass of 60 kg. The blades can be approximated by as thin rods which rotate about one end, often perpendicular to rotate about one end of an axis perpendicular to the length. The helicopter has a total loaded mass of 1200 kg. Calculate the rotational kinetic energy in joules in the blades when they rotate in 300 rpm. So this is the helicopter having 4 rods. Now, how to solve it will show below. So this is question number 6. So we know that first of all we have to calculate the rotational kinetic energy of the helicopter. Rotational kinetic energy I am writing in short as rotational Ke, and that formula is half I omega square. Omega is the angular velocity and I is the moment of inertia. So to get to that you have to first know what is omega and what is I. Now in the question it is written down that omega is 300 rpm, or rpm is basically revolution per minute, but you have to convert it into radian per second so that you can deal with the same unit for all of the values, same standard unit. So 300 rpm, how do you convert into radian per second is that this is 300 revolution by 1 minute. Now 1 revolution is full circle is 2 pi. So 300 is 300 into 2 pi radian divided by 1 minute is 60 seconds. So if you solve this, you will get that this is 31.4 radian per second. This is your omega. Now what is the moment of inertia of I? So moment of inertia is basically coming from the okay, just 1 second. So now the moment of inertia will be coming from the rod or each of the helicopter wing basically. So because there are 4 rods, so there will be I rod into 4. Now each helicopter blade, basically each blade is considered as a thin rod of same mass for all of them, mass same, rotating about an axis placed at the end of the blade. So you already know that the formula how to derive the moment of inertia for a single rod, but there can be two cases. Either the axis of rotation is passing through the like center of the rod and perpendicular to it, and the other option is the axis is passing through one end of the rod and perpendicular to it. Like in this case, let's say let's say this is your rod, okay, and if the center is passing axis of rotation is passing through this like this, so it has a rotation not like this but about this axis, and the center is this, okay. So in that case the inertia will be m L square by 12, where 12 L is the total length of the rod and m is the mass of the rod. But for case 2, which is our case, is that this is the rod, vertical rod of length L and mass m, and the axis of rotation is perpendicular to the rod, this dashed line, but this is at the center, not at the center but at the end of the rod. So in this case the moment of inertia will be ml square by 3. So if this is the case, then for 4 rods that will be 4 ml squared by 3, the total moment of inertia, right? So you can put the values that m equal to 60 kg and L equal to 4 meter whole squared divided by 3, and you can calculate the moment of inertia to be 1280 kg meter square. So this is an SI unit right now. So the rotational kinetic energy in short will be half into I is 1280 kg meter square in SI units into omega squared is 31.4 whole squared radian by second whole square. So this kinetic energy value, if you calculate, it will be 6.3 into 10 to the power minus 5 joule. So energy is coming in SI unit of energy, which is joule. So this is your answer. So we calculated it to be, I think, what was that, 6.3 10 to the power 5. So 6.3 into 10 to the power 5 means 6340. This joule. So this is within this range, that is the accepted answer. So this is right. Now question number 7, an air table is used to study the elastic motion of flexible spacecraft models. Pressurized air escapes from numerous small holes in the horizontal surface. It provides a supporting air cushion which largely eliminates friction. The model consists of a cylindrical hub of radius r and for four appendages of length L and small thickness T. See figure. So the center part, there is a hub. Okay, so this is the hub. Sorry. This is a hub where the hub has a cylindrical shape with a radius of r. So this radius, this will be r. And four appendages, these are the four appendages, this in green. They have length L and small thickness T. So this small, they are very thin, their small thickness is T like shown here, and length is L. Okay, and their width is D also. And the hub and the four appendages all have the same depth D. That means this is also D, and this height of the central hub is also D. And this is also D. So, and constructed of the same material of uniform mass density rho. This is the volume mass density. This is same for both the hub and the four appendages. Now assume that the spacecraft is rigid. The moment m, which must be applied to the hub to spin the model from rest to an angular velocity omega at a time period tau, is what? So here note that for a spacecraft with highly flexible appendages, the moment must be judiciously applied to the rigid hub to avoid undesirable large elastic deflections of the appendages. So once you understand what is the picture here, we will move downwards and try to solve this. Question 7. So there is a cylindrical hub sitting, and it has a radius of r, it has a height or depth whatever is d, and from there are four, again there are four such appendages. So this depth is also d, and this thickness, the small thickness is t, and this length is L for all of them. There are such four blades or appendages, not blades. I don't know why this is not erasing out. Let us just ignore this. There are also part of the appendages. As you can see from the figure, I am not drawing a 3D diagram here. But the main idea is that this is the perpendicular axis or z axis. And let's say this is x and y. X, y, and z. And there is an angular rotation omega for this place. So now the central half has a mass, okay, and the base of the appendages has a different mass. So central halves mass equal to mh for half, and each blade's mass, there are 4 of them, each blade mass is mb. Okay, and because rho is uniform and common for both of them, mass density, so mh equal to simply the mass density rho into the volume of the central half, which is basically it's a cylinder. So cylinder half volume to pi r square into d. This is pi r square. But the mass of the blade, each of the blade is this is like a 3D rectangular cube, not cube but 3D dimension, which has all 3 dimensions given, like this length is L, depth is D, and thickness is T. So this is simply rho L T B. Okay. So then what was the question? So let's read the question again. So the question was, the moment must be applied to the half to spin the model from rest to an angular velocity omega in a time period of tau is how much? So first of all, okay, so let's say what is the formula for angular acceleration? Angular acceleration is represented by alpha. Alpha is equal to basically omega by tau, because omega is the angular velocity and this is the time in this case. Because you know that acceleration is meter per second square in linear acceleration, that means it is length by time square. In other words, it is velocity by time, because velocity is length by time. And similarly, in angular case, angular acceleration is also angular velocity by the time tau as given in the question. Now, what is the moment's definition? What is meant by moment? So, moment is basically nothing but a product of the moment of inertia and the angular acceleration. So, moment basically means moment of force or torque basically. In angular case, obviously. Normally, linearly, you know that F equal to m times a, where m is the mass and a is the linear acceleration. But here the moment of force or the moment is basically in angular case. So that will be a moment equal to Izz into alpha. Now why such a thing is chosen? Because Izz is the moment of inertia about z axis, which is valid here because the whole thing is rotating about z axis. So effectively z axis is about is the moment of inertia needs to be taken. So rotational axis z axis. So inertia about z, and you know that in angular sense inertia is equivalent to mass for angular case, and alpha is angular acceleration. It is equivalent to linear acceleration, not equal, this is equivalent to sign. So by that thing, like you have F equal to ma, similarly the force moment m equal to Izz into alpha. Now what is IZZ? IZZ is clearly the moment of inertia of the whole configuration with respect to Z axis, which means that it consists of two parts. One is the moment of inertia about Z for the cylindrical hub at center, and the other is moment of inertia from the four blades about Z axis. This is the moment of inertia about Z axis for Z plus the moment of inertia four blades around about the Z axis. So IZZ equal to will be, what is the moment of inertia about Z axis for a cylindrical hub at center. So for this case, you know, for cylinder the inertia about the axis of rotation is just half mr square. So in this case half mass is mh into r square, because r is the radius of the hub, plus because there are four such blades, so four times the moment of inertia for the blades, and you know that has components like 1 by 12 md L squared plus md r plus L by 2 whole square. And why such a thing we have to do is that we are choosing the axis of rotation universally for Z axis here, situated here, for all the four blades and the cylindrical hub. But there is a but, that for each of the blade the center of mass should be, sorry this vanished, I don't know why. The center of mass should be passing through the center of the blade like this dashed lines. Okay, and they will be rotating effectively about this direction, right? So this is the center of mass exactly at the center. So this length then becomes, the whole length is L, then this length is L by 2. And this length from center to, sorry, basically not here, but here this is the extended part of it. This is R, because that is the radius of the cylinder. So now you have to express everything in terms of rotation about this central axis. So whether your rotation of the blades is about this axis through to that passes through their center, but you have to apply the parallel axis theorem and convert it into a moment of inertia about this Z axis here. Okay, so to do that, what we will do is that half mv L square, this is the moment of inertia of the blade, like treated like a rod of length A, mass mv, and the axis of rotation is passing through the center of the rod. So in that case, you already know the formula, that is not half, it is 1 by 12 RB MB L squared. But there is also this parallel axis theorem thing, that by parallel axis theorem, the moment of inertia about central Z axis equal to moment of inertia along Z about axis through mid of the rod plus m, where in this case the blade has a mass md, so plus mv times the distance between the two axes, so which is in this case is r plus half L by 2 whole square, because already this length was L by 2 and this length was given as r by the question. So from this center to this center the length is r plus L by 2. So this we mark as question number 1. Now total Izz will be half mh r square. Mh was already calculated to be rho pi r square d. So this we are using this mh, and next we will be also using mv values. So this is half rho r square d times r square plus 4 1 by 12. mv is rho l td, rho l, then again d, then l squared, plus mv r plus half r plus l by 2 whole square, plus mv is rho l td r plus l by 2 whole square. So this is equal to half rho pi d r to the power of 4. 4 rho td l common. This is l squared by 12 plus this thing goes in common. So this is r plus l by 2 whole square, which is r square plus l square by 4 plus 2rl by 2, or simply rl. Okay, so what we are getting is that half rho pi d r to the power 4 plus 4 rho t dl l square by 12 plus this is, I think this is r squared plus l squared by 4. So r squared plus l squared by 4 plus l squared by 12 plus rl. So further simplifying, half rho pi r to the power 4d plus 4 rho l td. This is plus rl. So this is l squared by 3 then. So the final answer is half rho pi r to the power 4d plus 4 rho l td to l squared by 3 plus r squared plus r. So this is your final answer. Let us go back and check. Okay, and another thing is that in this question, apart from this thing we have used, we have half rho pi r to the power 4d. So if you want to express some parts in terms of omega, then what is omega? Omega is basically alpha times tau, right? Because omega equal to alpha tau. So in this case, it will be half rho d so yeah, so basically the question was the moment must be applied to spin from rest to an angular velocity omega. So what we have calculated till now is the moment of inertia basically. So to calculate the moment, basically the moment of force, you need to multiply the IZZ with the alpha. So that was the missing part that we did not do before. So we have calculated earlier the IZZ value. Now moment will be similar to torque, which is IZZ times the angular acceleration alpha, right? And alpha, the angular acceleration, is omega by tau. So this is IZZ omega by tau. So this is IZZ value you put. This is rho pi d r to the power 4 omega by tau plus half plus 4 rho L Td square by 3 plus RL plus R squared into omega by tau. So this is equal to, you take out common as omega rho d. The first term is half pi r to the power 4. Second term is 4 L T, then 1/3 L squared plus RL plus R squared divided by tau. So this is our answer of the moment or moment of force, which is same as this given answer. So this will be our correct answer. So now question number 8 is that a mass m travels at speed perpendicular to a stick of mass m and length L, which is initially at rest. The mass collides completely inelastically. This line is important. Inelastically collides with the stick at one of its ends and sticks to it. So the mass has been stuck to the stick. Now before and after the collision, which of the following statements is true? So the options are about momentum and energy conservation, and momentum, angular momentum conservation, etc. So in this case, because this rod was initially at rest and this was its center of mass, now this mass of m is traveling perpendicular to the stick with a speed v0, and it hits or collides with the stick and it gets stuck at the end of the stick, and in the process also rotates the stick a bit. So that is why the angular rotation omega is there, and the center of mass has also been shifted from the this center of mass has been shifted from this point up to this point. This is the new center of mass, because obviously the center end point has now extra mass of m, so the center of mass should be shifting downwards from the center. Now because it is mentioned that it is a complete inelastic process. So for inelastic process, you know that your angular momentum and momentum both will be conserved. So okay, so with this we have finished all the 8 questions for this tutorial, and this is the final tutorial of this course.